Hello, welcome back to Physics 122. So I just want to make a final remark here on the thermodynamics, on the chapter of thermodynamics in the building blocks of physics. We did cover the zero law of thermodynamics. We went through the details of the first law of thermodynamics. And there are lots of problems that can be solved using the first law of thermodynamics. I briefly mentioned the third law of thermodynamics. And what I didn't mention was the second law of thermodynamics. I didn't mention this law because we skipped that part of the book that the law is mentioned in the section of entropy. Okay, so I just want you to expose you to the second law of thermodynamics. The entropy of the universe never decreases. There is a mathematical definition for entropy, but it can mostly be interpreted as entropy can be interpreted as an order and disorder of a system. Okay, so entropy is a measurement, here you go, of the disorder of a given system. That's how you quantify, that's how you qualify entropy. Mathematically, that's the definition of entropy. The heat divided by the temperature, okay? If an amount of heat Q flows into a system at constant absolute temperature, don't forget constant temperature, the entropy change of the system is equal to that. So it's just a matter of, entropy is just like an interpretation of the disorder of the system. Qualitatively, that's how you should interpret that. That's the only thing that I want to point out on this chapter. So now we are going to skip to electricity and magnetism. Here you go. I already covered some of them in the lab. Electric forces and fields. So we cover only electric forces. We covered the electric charges. We covered electric forces. We didn't cover electric field yet. So go ahead and refer to the lab videos that we have on Coulomb's law and also on electric charge. Right? So let me just, here you go. Let me go just quickly here. So now we're going to talk about electricity. Some of this material we already covered in the lab. What did you cover in the lab? We covered electric charge and we covered electric force, which is Coulomb's law. So we can refer to the videos on my YouTube channel for the lab. Let's take a look. Thermodynamic processes, first law, capacitors. You don't want to read capacitors. You want to refer to this one right in here. Okay? Lab, Coulomb's law. I gave you the background theory here during the lab. The background of the theory during this lab. So take a look on this video. I'm not going to repeat myself on that, okay? And let's go back here to the chapter of the book, electric charge. You already know about the electric charge. There are positive and negative electric charges, and there is also the neutral electric charge. The basic negative electric charge is the electron. We have the proton as a positive electric charge, and you have the neutron as a particle which is a particle that has no electric charge whatsoever. Just like mass, the electric charge of a constant system never changes. That's what we call the conservation of charge, law of conservation of charge. And you also have the law of conservation of mass. Electric charges are not going to pop out in your system out of nothing, okay? And here we go. We have positive and negative charge. The elementary electric charge is that the value of the elementary electric charge is the value of the charge of the electron and the proton. We haven't observed electric charges that are less than that. Experiments show over and over again that the lowest electric charge is has this value here. And you not only this value, but is an integer value, is an integer multiplicative factor of this value here. You're not going to see in nature an electric charge that's 1.7 times 10 to minus 19 coulombs, or 1.8 or 1.9, but you're going to see 3.2 times 10 to minus 19. You're going to see 4.8, which is 3 times 1.6, and so on. Okay, so look here at the masses, the electric charge of the electron, right? And the proton, they are exactly the same charge with a different sign. Okay, but look at their masses. The proton mass is almost 2,000 times more than the electron mass. Okay, so a very important difference of this between this concept of mass and the concept of electric charge. Those two concepts, those two ideas are not the same. They're different. They're very different. You can have a particle with the same electric charge, magnitude, right? The same magnitude of the electric charge, but having mass that are different, completely different. The neutron has a charge that a little bit more, greater, a little bit greater, has a mass that a little bit greater than that of the proton. But it's almost the same. See that the difference? And a charge is going to be 0. I'm just doing that quickly, right? Because we already done that before. You can do those examples that you have here. Polarization. What is polarization? It's possible to separate the negative from the positive charges. If you get a rod, for instance, that electrically negatively charged, this rod can attract the positive charges of paper bits, provided you don't touch the paper bits. Those two, the positive charge is going to be separated from the negative charge. That's what we call polarization. Negative end up in one side, positive end up in the other side. Okay, it's possible to do that. Not only is it possible to completely charge an object with a net charge negative or a net charge positive, it's also possible to polarize an object. Polarize means separate the charge, the negative from the positive charge. The net charge of those paper bits are still 0, but you manage to separate the charges. You manage to polarize the object. A very good example of a polarized object is the molecule of water. The molecule of water looks just like that. Electrons spend far more time orbiting. If you molecules of water is made of 2 hydrogen and 1 oxygen, right? So the electrons of the hydrogen atom spends far more time orbiting the oxygen atom, producing a polarization in the molecule. Okay? Producing a polarization in the molecule. A separation of electric charges. That's a good model of the water. And because of this polarization, water molecules, they attract one another. The positive side of the water molecule is going to attract the negative side of a nearby water molecule. See that? The hydrogen facing the oxygen, and you have another hydrogen facing the oxygen here. It's a weak bond, but there is a bond in there. It's called the hydrogen bond between molecules. Here the bonds are covalent bonds within the molecule. So that's the first section of the book. What you have to know also, I mentioned that in my lecture before, we have electric conductors and electric insulators. Electric conductors, they manage to conduct electrons more easily than electrical insulators. Electrical conductors, they have what we call free electrons, just like in the free electrons in metals. They can move very easily from one point to another in the material. Whereas insulators, the charge tends to remain in a single spot of this insulator. Okay? So here you go. Let's see if we have an illustration here. Here you go. Here the case of a metal sphere. Okay? And here's the case of a metal rod. When we have not a metal rod, but a glass rod. When we have a glass rod here, we charge this glass rod, we have an accumulation of charges in this case, in this illustration, at the tip of the rod. The charges do not distribute evenly throughout the rod, throughout the glass rod. That's a characteristic of an insulator. In the case of a sphere, of a metallic sphere, of a conducting sphere, if we approach this glass rod to the metal, the metal sphere is initially uncharged. The amount of electrons is the same as the amount of the protons. When we approach the charged glass rod, we cause the sphere to become polarized. You see the polarization here? The positive charges attract the negative charges of the metal sphere and repel the positive charges of the metal sphere. That's why you see the positive charges right in here. So when we touch the rod to the sphere, what's going to happen? The negative charges in the metal sphere is going to migrate to the glass rod. But you have to touch it. Okay? And when that happens, we have the sphere becomes with a larger number of protons. We have that the sphere has become deficient of electrons. So the sphere ended up becoming positively charged. The sphere has been kept in an insulating base, so there is no leakage of charges. The moment I withdraw my glass rod, all those positive electric charges immediately redistribute within the conductor. Okay? They don't stay concentrated in a given spot. That's the difference between metals and conductors. That's the difference between conductors and dielectrics, insulators, electrical insulators. Keep that in mind. Immediately those electric charges become distributed throughout the conductor. Whereas in the case of a dielectric material, an insulating material, electrical insulating material, the charges become concentrated only at a given spot. They don't move easily through the material. I mentioned that as well, right? During the lab. Here we have charging a conductor by induction. We can skip that. There are ways to electrically charge materials. And that's by Coulomb's law. We cover Coulomb's law as well. Okay, here you go. Here's the law that I mentioned to you before. The constant K. An electrical force is a vector, just like the gravitational force is also a vector. So because it is a vector, when you have a distribution of electric charges that I have here, okay, let's take a quick look at that example. 3-point charges, okay? What's the force Q2 do to the other two charges. Let's see, suppose 3-point charges are arranged. A charge Q1 is this one here, is located at the origin of the coordinate system. A second charge Q2 located at this point, and the third charge is located at this point. The charges are fixed. They are not moving. They're not free to move. What is the force on this charge? What's the net force on this charge? Right? That's what he's asking. It's going to be an attractive force due to Q3. It's going to be an attractive force due to Q1. Note, see that those two force vectors are not perpendicular to one another. They make an angle. Okay, and then you have to calculate, here you go, force of 2 in 1, force of 2 in 3, force in 2 due to 1, force in 2 due to 3. Okay? That's the net force that we end up getting, and you have to calculate this force in this example. You can break down this force into x and y components. And when you do that, you can use the Pythagorean theorem to find the net force. Okay, he does that everything. Here you can review that. You can even get the angle of the force. That's another problem that you can think of: two charges that are electrically charged. The balls are charged, after which they hang apart. The angle measured is 15 degrees, this half angle. From the vertical, 10 grams each ball mass. Are the charges of the same or opposite? Well, if they are repelling one another, that's because the charge is the same, right? But the magnitudes are not necessarily the same. The forces are the same, even if the magnitude of the charges are different. And so you have to use, here you go, you have to use a free body diagram. He's asking you what's the magnitude of the electric charges. Okay, so you have the weight of each ball, you have the electric force, you have the tension. It's going to produce two equations, only along the x-axis, the other along the y-axis. That's what free body diagram is going to produce. You have the theta angle that was measured. Okay, so here you go. I'm just quickly do the force along the x-axis, the force along the y-axis. Tension, electric force. Let's see what happens. The mass we know, we do not know the tension, right? We do not know the tension. We know theta, but we do not know the charges. Q1 and Q2. Tension is a unknown, Q1 and Q2 is a unknown. It's three unknowns in this equation. Let's see if we can solve it or not. Okay. Let's see, but wait a minute, he's assuming that the charges are the same, right? At first glance might appear that the charge must be the same. The balls are hanging at the sun. It might appear. So there is no clue that which charge is larger, but looking again at Coulomb's law, the force on either of the balls is proportional to the product of the two charges, according to Newton's third law. Coulomb's law said the two forces that make up the interactions are equal in magnitude. Okay, the charges are not necessarily equal. Okay, the charges are not necessarily equal. Let's see what he's asking on C. Let's go back what he's asking here on C. Find the net charge on each ball, assuming that the charges are equal. Okay, assuming. Okay, if we assume that the charges are equal, so now we have two unknowns: the tension and the charge. Okay, so in general, the charges are not necessarily the same. But assuming that the charges are equal, we can solve the problem because we have two equations for two unknowns: the number of The nonce reduces to 2. So here you go, we have this electric force here, right? And then we can solve our system of two equations for two unknowns. Okay, the distance between the charges are the 2 times the sine of theta. And we solve for Q squared, 0.22 microcoulombs. Okay, and then we have another problem for 3-point charges. So that's what we have for this chapter. And now that's the material, the new material that starts. We start with this new material right now. So let's just document everything that we said, right? I'm going to start here with the thermodynamics. Thermodynamics, two new basic quantities. And what are those two new basic quantities? The temperature and the amount of a substance. The unit here is the mole, and the unit here is the Kelvin. What else do we need? What else we have to know about thermodynamics? We have 4 new laws. The zero law, a statement about thermal equilibrium. That's what it's all about. This is important if you're going to use thermometers, if you're going to build thermometers. Just that statement about the zero law guarantees to you that a given thermometer can measure the temperature of two different objects. If two different objects are at the same temperature, means that those two different objects are in thermal equilibrium with each one separately as well. That's what the first law of thermodynamics is all about. The first law of thermodynamics is the one that we use the most. The first law of the thermodynamics is, I'm going to just copy from what I had before. First law of thermodynamics, what? The change in internal energy is equal to the heat applied. Change of internal energy of a system is equal to the heat applied to the system plus the work done on the system. The second law of thermodynamics I didn't cover well, but it has to do with entropy. Order and disorder of a system. And then we have the third law of thermodynamics. It's about no object can reach absolute zero. The most important of those 4 laws is this one here. This one that I'm going to do. This is the one that I'm going to use to solve most of the problems in thermodynamics. Okay? And now that we start looking into electricity, we have a new basic quantity, that is the electric charge. The unit is the coulomb. I hate that when he does that. You know, I'm going to put it 4 laws. 4 laws of thermodynamics. And then electricity. We already saw one of the laws of electricity, Coulomb's law. So you may ask yourself whether there is no other thermodynamic laws missing from my list here, you may ask yourself whether, aren't you missing the ideal gas law? No, no, I'm not missing the ideal gas law, because the so-called ideal gas law is not a law per se, okay? The so-called, let me write that down here for you, the so-called ideal gas law, it's not a law per se. It was a law in the past. When it was discovered, it was a law, yes. That's why I like to refer those things to quote law. Watch out for that. Okay? Wikipedia has a very good article on that. Take a look here on ideal gas law in Wikipedia. Ideal gas law, also called the general gas equation, is the equation of a state of hypothetical ideal gas. Now, here you go. It is a good approximation of the behavior of many gases. Just the fact that it says a good approximation, it eliminates the fact that this thing is an actual law. It's a law only in the name. For historical reasons, we preserve this term law. And I can say that this name here, general gas equation, is far more accurate than the ideal gas law. Okay, it's a good approximation of the behavior of many gases under many conditions. A law is not a good approximation. A law is something that happens, that can be stated all the time. Okay, only in extreme situations a law, a physical law, breaks down. Only in extreme situations. But this one is breaks down for any type, for some gases that are not ideal. Okay, although it has several limitations. See that? Another indication that ideal gas law is not a law. It was first stated by Benoit Paul Emile Clapeyron in 1834 as a combination of the empirical Boyle's law, Charles' law, Avogadro's law, and Gay-Lussac law. Okay, and then there is something else interesting here. Let me show you. That's going to put the nail in the coffin of the law, of the ideal gas law. Okay, it says here, molar form. Let me show you that to you. Statistical mechanics, right in here. I want you to read that. In statistical mechanics, the following molecular equation is derived from first principles. It doesn't say what the first principles are, but that's the equation that is derived. Does it look like the ideal gas law? It doesn't look like the ideal gas law, but if you keep on reading, you're going to see where P is the absolute pressure. Okay, we have the absolute pressure in the ideal gas law, again in between quotes. N is the number density of the molecules. Okay, it's not the number of moles. And the number density of the molecules is given by N divided by V. So we do have a volume term here that will be big N divided by big V. So this V goes to the left side, becomes PV equal nRT. Okay? The big N combined to KB turns into NR. Okay, folks, so again, the ideal gas law is not a law, so it shouldn't be listed in those 4 equations that I showed to you. So what else we have to talk? Okay, we have to talk about the electric charge, right? Here you go. And in electricity, we have the Coulomb's law. So let's continue here. We talked about the electric charge. We talked about the electric force. Here you go. Here is a basic quantity. And here is a law of physics. What comes next is not a basic quantity nor a law of physics. What comes next is a convenient definition that's derived from electric from the electric force, from the equation of the electric force. What comes next is called the electric field. Okay? It's a quantity that's very useful. And let me illustrate to you exactly what this electric field is all about. There's a very nice qualitative way of understanding it. In order to understand what the electric field is, we have to start with the electric force. Okay, think about, we have this charge here, the origin of the XY coordinate system. And think that we have another electric charge somewhere around here. Okay. So we can illustrate like the following. Here we go. Right, those charges, both charges are placed here in space. Okay. And then what comes next? There is a force of repulsion between those two charges according to Coulomb's law, right? If I move this charge elsewhere, I'm going to move this charge elsewhere. Okay. I find out that the force changes direction, right? If I did everything right, here you go. It's going to be like that, this force, right? In this direction. But don't forget, the force is applied to that other charge. I'm just doing that to get the right direction of the force. Here you go. Okay. What you see, okay, this force is in there because the electric charge is in there. What happens if we remove the electric charge from this spot like I did before? We are no longer going to have an electric force, right? We have an electric force only if the charge is positioned in space. We may not have an electric force, but something else is left behind. Okay? This something else has a name. This something else has the name of an electric field. It is as though the electric force is a ghost of the electric field, is a shadow of the electric field. Is a shadow of the electric force. Something that was left behind when we removed the electric charge. Okay? Oh, let's take a look. Here you go. That's what this red arrow is all about. This red arrow is a representation of the electric field. Whether it's in that first charge, whether it's in the second charge, whether it's in the third charge. And the direction of the electric field is defined by what we call a test charge, which must be a positive charge. That's how you find out what's the direction of the electric field. You must put a positive test charge in place to find out the direction of the electric field. That's how the electric field is defined, okay? It's a vector quantity which can be represented either by vectors, like you represented here, or can be represented by lines, like we represented here. It's much easier to draw a line of electric fields than to keep on drawing electric field vectors all over the space. It's far less work, far more convenient to do something like that, to make a drawing like that, than to make a drawing like that. Okay, so that's the qualitative idea of the electric field. I can say that the electric field is a ghost of the electric force. That's a good way of defining it. Is whatever is left behind. Electric field is whatever is left behind whenever we remove an electric charge that was feeling a force. That was experiencing a force. Okay. So let's write it down. What is the electric field? What is the electric field? Well, the electric field, I like to define it, is a ghost of the electric force. Something that is left behind when we remove a second charge from space. Okay, so let's go step by step, right? If you put two electric charges separated from one another, a main charge, which can be either positive or negative, which can be either positive or negative, and a secondary charge, which must be positive. We notice that there is a force applied to the secondary charge. Okay, so the steps are like that. I'm going to put it even simpler than that. Put two charges separated from one another. A main charge and a secondary charge. Let's make it simple, right? Here you go. Main charge can be either positive or negative. Here you go. The secondary charge must be positive. That's how we define the electric field. It's the force in a positive test charge. The secondary charge, also called the test charge, must be positive. Okay, put two electric charges separate from one another. I mean, charge and secondary charge. Here you go. Monitor the force applied. Look at do not monitor, but look at the force applied to the secondary charge. Okay, remove the secondary charge from its original position. Okay, what is left by removing the charge? No force. Okay, here you go. By removing this charge, no force vector is left behind. Instead, what is left behind is something else we call the electric field. Okay? So a good way of defining the electric field. Here you go. So what's the electric field? Electric field is the ability that a given main charge has to exert a force at a given point in space. That's what it is. That's how you can think in terms of the electric field. It's the ability that a given charge has to exert, right? To exert a force at a given point in space. So let's go back here. Here you go. Here we do not have any force whatsoever. We don't have any force because there is no electric charge here at this spot. But if we put an electric charge here at this spot, there will be a force. And this electric field is just reminding you that you may have an electric force here at this point in space. And this electric field is something that we can really measure. Okay, it's something that we use in physics. It's not just something that is invisible but doesn't exist. Oh, it is invisible, yes, but it does exist, and it's a very useful idea that we use every day with our cell phones and many other things. Here we go. If the main charge is negative, the electric field lines point and the electric field vectors point towards the electric charge. Okay, let's get, here we go, that the electric field vector should be a negative charge. Okay, so here we go, we have anything else? Okay, we're gonna get, oh yeah, here you go. Now suppose that we have two electric charges. Okay, they are both, let's see, they're both positive. Okay, the electric field due to this electric charge on the left is going to have a direction like that. So do you see they have the same value? The electric charge, those two charges have the same value. And, oh gosh, I hate that when that happens. Here you go. And so we have the second electric charge that's also positive, that's producing an electric field away from the charge. So here you go. It's minus A on the left side, right? Let me correct that. Here you go. Gotta fix that. Minus A here. Minus A here. Oh, the charge is positive. Both charges are positive. Okay. Minus A here again. Fix, fix, fix. Electric field. Electric field. Electric field is a vector. Notice that I drew the electric field. This electric field has the same length as this one, because the distance from here to here is the same as the distance from here to here, and the magnitude of the charges are the same as well. So much that I gave them the same letter. So those two electric fields, they add to one another, producing a net electric field. Okay, but let's see what is the equation for the electric field. What's the equation for the electric field of a point charge? Okay, the equation for the electric field of a single point charge is derived from Coulomb's law. And it's given by, here you go, we gotta get that equation for the electric force. Well, I gotta do that all over again. Insert, gonna be too much trouble. to get it. So here you go, electric field. Whoop. It's gonna be what? K Q divided by R squared. Okay? That's the magnitude. But if you want to put that in vector format, it's going to be like that. The symbol of the vector, and we must put a unit vector R right in here. R hat. This unit vector hat R goes from the charge to the point in space, just like you saw in my drawings right in here. Oh. Okay, let's go here. See that? So if you want to know the electric field, the direction of the electric field, at this point, it points towards the electric charge. Here we go. Like that. The further away, notice that the further away, according to the mass, right? The further away you are from the charge, the lower the electric field is. That's the mathematical definition of the electric field. Let's take a look here at your book. Oh, that's not the book. That's, yeah. Oh, and, oh yes, that's a very good analogy. What's the analogy between the electric field and the electric, and the gravitational force, right? Let me spell that out to you, by the way. Going back here, right? Just remember that the electric force is what? The electric force is big Q is small q, R hat, R squared, divided by R squared. So the electric field is going to be what? The electric field is going to be the force divided by the value of the test charge. That's what the electric field is all about. Recall what we had for the gravitational, the analogy for the gravitation. This is analogous. This is analogous to the gravitational acceleration in the law of universal gravity. Okay? So in the law of universal gravity, what do we have? Here we go. In the law of universal gravity, the only difference is going to be the negative sign here, and big G. You have a big mass. We say we have a small mass divided by R squared. Okay, so the gravitational acceleration. What is the gravitational acceleration? I'm going to write it down here for you. Here you go. The gravitational acceleration is small g is going to be what? Big F divided by m. Okay, that divided by m, which ends up being m and m, like that. Gm over r. So that's the analogy between the electric field and the acceleration of gravity. The difference being that for the electric field we can have positive and negative charges. For the gravitational acceleration we have, for the gravitational field, which is, by the way, is the gravitational acceleration, we have only positive values for the mass. So according to this definition of the electric field is unit is Newton per Coulomb. Let's do that. Let's document that. Go. Unit of the electric field is here you go. We put that the representation of unity is the quantity in a square bracket. Newton per Coulomb, like that. What's important to note is that this idea of field is not restricted just to the gravitational field or to the electric field, but to any type of field. Okay, so a field is the force. Here you go. You see here, right? Is the force per unit of the source. Okay, here you go. The source of the electric field is the electric charge. So is the unit of the electric field is Newton per unit of electric charge. The source of the gravitational field is a mass, so the unit of the gravitational field is the force per unit of mass, which ends up being, in this case, meters per second square. So let's take a look and go. Here's the case of a charge, right? BQ charge. It is applying an attractive force to a positive charge that's placed around it. The force is attractive, and consequently the electric field must be towards the primary charge. So we can also here write the electric force in terms of the electric field. Let's do that. Here you go, right in here. You're going to be doing that all the time, okay? The electric force can be here written also as the charge times the electric field. Like that. What does it mean that the electric field is the electric field that the location due to all other charges? Well, you may have all charges, you may have other charges around it. Okay, just like that example that I showed to you, right? This one right in here. If you have two charges, the electric field at this point is going to be something like that. And then you can go ahead and keep on playing with electric fields. You know, let's see, this one here. Now we have a negative charge. Okay, here you go, should be a negative sign. On the right side, a positive charge on the other side. So we can go ahead and figure out what's going to be the electric field at a given point here along the y-axis. The electric field of the positive charge is away, right, from this charge. The distance of this charge to this point is the same as the distance of this charge to the other point. Okay, here you go, angle theta. And here you go. That's the orientation of the electric field of the negative charge. Compare that with the other one, that was the positive charge. Oh, gotta fix that. Here you go. Okay, so compare that with this one here, right? Positive charge, both positive charges, the electric field points upwards. One positive charge, one negative charge, the electric field points sideways. The electric field points sideways in the horizontal. Here you go. Here you go. That's the net electric field. So you can have a bunch of electric charges distributed in space, and you can find out the electric field at a given point. So let's go ahead. Let's fix all of that, right? Yeah, negative, negative, negative. Oh, another negative here. Another. If you want to figure out what is the electric field at more than one point in space, right? That's the first point. That's the, let's say, a second point. Let's take a look. Which one? No, that's the first point. This one is the second point. Further away from the origin, you should expect that the net electric field should decrease because the distance is different. But if you're going to find the electric field at a different point, like this one right in here, it's not going to be in the horizontal direction, because now this point, this point right here is further away from this charge than from this charge, and there won't be a symmetry along the y-axis like there was a symmetry along the y-axis here, right? So the net electric field will tend to point more toward this charge right here. So you can play with things like that to have a qualitative idea of what the electric field distribution is all about. Okay, so now when you have two charges, one negative and the other positive, we call this distribution an electric dipole, which is represented by a vector going from the negative charge to the positive charge. That would be the representation of the electric dipole, an arrow. Okay, electric dipole, net charge equal to what? 0. Q plus minus Q. But we can also have what we call an electric not electric dipole, but an electric quadrupole. Net charge is still 0. But now the electric dipole ends up to be 0 as well. So here we go, we have this charge Q greater than 0 on the left side. We have this another charge plus Q, positive charge at A. And then we place a big charge minus 2Q at the origin. Okay, if we break down this minus Q charge into 2 minus Q charge, it is as though as you have one minus Q charge teamed up with this other one, and the other half of this charge teamed up with this other one. Two electric dipoles, one electric dipole pointing to the right, another electric dipole pointing to the left. So this electric dipole vector cancels one another, and this charge combination becomes what we call an electric quadrupole. A very simple way of visualizing something like that. Okay, so when you go home, make sure you play with this type of configuration. It helps you understand better. Wait a minute. Okay, yeah, we have a minus Q here, right? And now this one is not an electric dipole because both charges are negative. Wait a minute. Yeah, there's something wrong here in this illustration. So let me point out there's a mistake here, right? If this guy is going to be positive, yeah, the electric field should be away. But if this guy is supposed to be negative, the electric field is wrong. It's not correct. The electric field should be pointing towards the charge. So let me just erase this one here, this graph. That's not correct. Here's the same thing, right? If this charge is negative and this other charge is negative, the electric field should be pointing towards the charges, and the net electric field should be downwards. Okay, so here you go. Like that, like that. And this one should be like that. Go. Here you go, like that. And the net field should be downwards. That's a correction that you gotta make. That's gonna be, the left field is gonna be this one, left charge, right? And the right charge, the field of the right charge is gonna be this one. Correction that we're making. I'm gonna erase this one. We don't need that. Okay. We don't need that either. It's just repetition. So let's go back to the book now. Charged sphere hanging in a uniform electric field. Okay, so let's say somehow we have produced an electric field here in this region, in this space. That's an example. Suppose somehow, doesn't matter how it was done, but somehow we produced a uniform electric field throughout the space in the horizontal direction. The sphere is charged. Okay, a small sphere of mass 5.1 grams is hanging vertically from an insulating thread that's 12 centimeters long. The insulating thread has to be, you must have an insulating thread so the sphere remains charged. By charging some nearby flat metal plates, the sphere is subject to horizontal electric field. So how do you produce this electric field, this uniform electric field? It's possible to produce a uniform electric field by putting two metal plates around here in this, one metal plate here and another here, and electrically charge those two metal plates. It's possible to do that. Connect a battery to those two metal plates, and then we can produce an electric field. Okay, that's why he said by charging some nearby flat metal plates. It's not shown in the drawing. This sphere is subject to horizontal electric field of magnitude 7.2 times 10 to the 5th newtons per coulomb. As a result, the sphere is displaced 6 centimeters horizontally in the direction of the electric field. What's the angle theta that the thread makes with the vertical? What's the tension in the thread? What's the charge on the sphere? Let's do that together. So here you go. I want to make sure I can get rid of as many of, here you go. Okay, I'm going to get rid of those. We don't need these drawings, but wait a minute. Yeah, I'm going to need part of the drawing. Let's take a look here. Here you go. I'm going to need the axis. Okay? Everything else is I'm going to keep my vector here, but the vector is going to be elsewhere. This is going to be my sphere. Let's see, this sphere is positive or negative? What is the charge on the sphere? Okay, I can tell you right from the bat that the sphere is positively charged. I can tell you right from the bat. Because the field is pointing from the left to the right, I can also tell you right from the bat that the plate here that's not seen is a positively charged plate. Okay? Why is that? Because positive charges are the source of electric field. Remember? We saw that before. Here you go. Let me go there before. Here you go. A positive electric charge are sources of electric field. What do I mean by sources of electric field? Okay, source of electric field means that the electric field comes out from the charge, comes away, produces the electric field. That's what I mean. Positive charges are sources of electric field, and negative charges are what? Are sink of electric fields. Just like the sink sucks the water, right? So negative charges are sink of electric fields. So every time that you see the electric field, you're going to know that the arrow of the electric field, the tip of the arrow of the vector of field is pointing towards the negative side, pointing towards a negative electric charge. And the tail of the vector is facing the positive charge, okay? So let's put that in the drawings here. We say that a positive electric charge is a source of electric field. In other words, the tail of the electric field vector faces the positive electric charge. Positive electric is a source of electric field, like that. Conversely, we say that a negative electric charge is a sink of electric field. In other words, the head of the electric field vector faces the negative electric charge, like that. So let's go ahead and do a drawing of our example. Okay, so I'm going to put here, did they say what was the charge, or what the sign of the charge? Let's see. By charging some nearby plates, he doesn't say, right? What's this as a result? Yeah, he doesn't say if it's positive or negative, but I can tell you right from the bat that the positive charge that's right here on the left side, the positive charged plate that's right here on the left side, is repelling this charge, and if it is repelling this charge, that's because this charge is positive. Similarly, the negatively charged plate is also attracting, simultaneously attracting. Not only this charge is being repelled by this plate that's here on the left, but is also being attracted by this other negatively charged plate. Okay, let's do a drawing. Here the X and Y axis, right? I'm going to come up with my insulating thread right in here. And I'm going to make it easy for me. Making as thick as I can. I don't need that. What else do I need? Oh, I'm gonna use this guy to represent my uniform electric field in space. Okay? What your drawing there in the book doesn't show is that in order to produce this uniform electric field in space, you must have a plate right here on the left side that's positively charged, and another plate on the other side that's positively charged. That's what those plates are doing. It's not there in the illustration again, and the book only mentioned that. I'm going to illustrate. Here you go, positive, right in here. And the other one, negative. Oh. Ooh. What I'm going to do here, make it a negative charge. The field, ooh, Jesus. I'm not going to put net field, I'm just going to put field of this plate. We know what the value of the field. That's the situation. Okay. So let's come up with a free body diagram. I'm going to simplify the drawing. I'm going to remove this plate here from the drawing. I'm going to remove this plate here from the drawing. And I'm going to remove most of the electric field lines just to simplify the drawing. Okay? The electric field. And I'm going to come up with I want to put this line somewhere somewhere here. Here you go. Okay, so here you go. I'm gonna that's what we call free body diagram, right? We want to find the charge Q. Let's go. I'm going to put different color. That's going to be the electric force. That's going to be the tension in the string. And that's going to be the weight of the charge. That's the electric field. I'm going to name all those forces. That's going to be the tension, right? That next one is going to be the electric force. And here is going to be the weight, the mass of the charge times the gravitational field. Free body diagram. Save that. Simple enough. So let's come up with our equations now. X-axis, y-axis. Let's go back to the problem. What is asking first? What is the angle theta that the thread makes with the vertical? Let's work on that now. I'm going to come up with a solution of example. $16.5. Okay, so here we go. We're going to have the following equation. Here we go. The mass is in equilibrium. Consequently, the net force must be equal to 0. Put the vector arrow there at the top. Don't forget to do that all the time. Right? Net force. And then we identified what the forces are, right? One of the forces is the electric force. Another force is the weight. Another force is the tension. So we deserve to have and to put an arrow in each of those vectors. Here we go. We have x-axis. Let's break it down into two equations now. X and y axis. Here we go. I'm going to do that with the software. Okay, I'm going to put not this what I want. Let's see here. Like this one. Here you go. Now I'm going to put two equations there. One vectorial equation, two scalar equations, right? Along the x-axis, along the y-axis. Here you go, x component of the electric field. X component of the weight. But the x component of the weight is going to be 0. Right? The weight doesn't have any x component whatsoever, but I'm going to write it anyway, just to emphasize it's the x component. And when we do that, we usually take out the arrow symbol from the vector. X component of the tension. Go. And we can do this one as well. Just substitute by, oh, don't forget to put the equal to 0, right? Here now is going to be replaced by y, and y. Okay? So now this single vectorial equation became two scalar equations along the x and y axis. The x component of the acceleration of gravity is 0, so this guy goes away, disappears. There is no, here, I'm going to emphasize it here that we have a 0 here. There is no y component for the electric field, because the electric field is only in the x direction, so this one is going to be 0 as well. Okay. I'm going to simplify my notation, because I want to put everything in the same line. Here you go. This matrix. Oh. Like that. So the charge is QE. We know the force is positive in the positive x direction. What about the horizontal tension? The horizontal tension. Let's go back to the drawing, right? The horizontal tension is in the negative direction. This horizontal tension must counter this positive electric force for the mass to be in equilibrium. Okay, so we're going to put a negative value here, and I'm going to emphasize, oh, one more thing, right? Don't forget what we have here is a theta angle. They're asking us to find the theta angle, right? What's the angle theta? So let's illustrate the theta angle right here. Here you go. That's not good enough, right? Let's see if we can get that a circle. Yeah, here you go. Black, thicker line. Here you go. I'm gonna make it a theta. Make it symbol. Here. So the x component of the tension is going to be what? Is going to be the sine of theta. Okay? This angle here is theta. Consequently, this angle here is theta. So the component, the x component must be minus t sine of theta. Becomes minus, I'm going to put it, remember, magnitude of the vector t magnitude equal this one, vector t sine of theta. I could have done that much quicker in that other software, right? But this one looks nicer. I don't need to repeat this zero anymore, right? Because the zero was already here. I don't need to repeat this zero here. But my acceleration of gravity in the y direction is minus g. And the y component of the tension, the y component must be positive to cancel the mg. If this charge mass is going to be in equilibrium, this x component must be equal to the electric field times the charge, and the y component of the tension must be equal to the weight of the charge. So here you go. Instead of sine, it's going to be cosine. Here you go, like that. Oh, I forgot to put the equal to 0, right? Two equations. I'm gonna bold-face the unknowns here, so you know what you're doing. The charge is an unknown, the tension is an unknown. The magnitude of the tension is also an unknown. Here you go. Oh, the theta is also an unknown, right? Let's see if we can solve this problem or not. We have three unknowns. Let's see here. The mass is known. The length by charging some electric field is known. What is the angle theta that the thread makes? What's the tension on the thread? What's the charge on the sphere? Yeah, it looks like we have three unknowns. Let's see how we can solve this problem. I'm going to boldface this guy as well. Hopefully there is a way to solve this problem. Okay. So what's missing here from this equation? We have two equations and two unknowns. So what's missing? Okay, we're not using everything. That's what we are missing. Okay, we are not using all the information that's provided by the problem. The problem provides us with the lengths. The problem provided with the horizontal displacement. So let's go ahead and add this information here. Here you go. The length of the string is L, right? And do you remember that was using the position A of the charge? So we know this length as well. So if you want to know the angle theta, all you have to do is to divide A by L. That's going to be the sine of the angle theta. So you don't need the free body diagram to find the angle. Okay? So here we go. To find the angle. Again, we are not going to need this to find the angle, but we can get to find the angle. Here you go. The angle. All you have to do is to get the sine of the right angle triangle. Display it in the book. Okay, so here you go. I'm gonna call that A divided by A divided by L is equal to sine of theta. And now I'm gonna use my software so I can go faster than that. Okay, I set up all my equations. I have everything in good shape here. Let's run my software. My favorite software. It's coming online. Here we go. Ideal gas. Now we're doing Coulomb's law. We're doing electric field specifically. Let's put that electric field for you. Okay. We started with angle A divided by L is equal to sine of theta. And we gotta write down the values of L and the values of A. 12 centimeters and 6 centimeters. $12 centimeters and 6 centimeters. Put here at the top, organize it neatly. A6, L12, we go. Okay, we solve for theta. Don't forget that this theta angle here is pi over 6. Okay, pi over 6 is what? Pi over 6 is 30 degrees. Okay, those are integer values, right, of theta. So let's write like that. Pi over 6 radians. Or, you know, theta is 30 degrees. I'm going to put that in degrees. So you find the first one. The next one is what's the tension in the thread? Now that we found what the angle is, we can find the tension, right? But then we gotta write down the equations here in my software. It's already there in my syllabus. My syllabus in my notes. The system of equations. Okay, we don't even. Yeah, you're right. Now we know theta, right? So we can use this equation here to solve the problem. So here you go. To solve the next item, right? Let's see if I can get that. Yeah, oh man, mg, what is that? Huh, interesting. Okay, you don't want, you want m times g. Here you go. T. I'm not gonna put magnitude here. I'm gonna put t. Yeah, it didn't copy well. T cosine of theta. Here you go. We want to find t. And now we go ahead and substitute the values. 9.8 meters per second squared. How much the mass? Mass is, oh, be careful, huh? Meter and mass, okay? So let's use a bigger m instead, so you do not mess up our, you know what, leave it small m here. And then mass is what? 5.10 grams. Okay, 5.10 times 10, I'm gonna put in kilograms, minus 3 kilograms. I don't want to mix up grams with g, that's why I'm doing that. And the theta, we already know, is pi over 6. I put those two right in here. Here you go. Start with 30 degrees. Oh, no, not 30 degrees. Pi over 6. We are now going to substitute for g. Oh, no, you cannot do that yet. Cannot do that yet. First, you substitute the mass. Otherwise, the meter of the g is going to mess up my mass, right? And now we substitute the g. Gotta be careful with that. Kilogram meters per second squared is up. Is it a Newton? That's what I'm getting for the force, a very small force. Let's see if it matches the book. Here we go. And let's see if the angle also matches the book, right? Let's see, 30 degrees. What about the force, the tension? First time I'm doing this problem, folks. If I got something wrong, he did, oh, 0.0577 newtons. Let's see, we got it. Yeah, I got it. 0.0577 newtons. And now what's the next? He wants the charge, right? What's the charge of the sphere? Okay, the charge of the sphere we get from the other equation that we discovered. Here you go. We get from this equation right in here. Minus tension equal to 0. And the electric field, the electric field is what? Go back to the problem here. Value of the electric field, 7.2 times 10 to the 5th Newton per Coulomb. 7.2 times 10 to the 5th Newton per Coulomb. Here you go. So I'm going to organize all that stuff. You know, I always like to put the nons, the equation below the nons, right? Here you go. What's non? Like that. I'm going to use the theta. I'm going to use the electric field right in here. Substitute all of that, and then I'm going to use the result that I got for the tension as well. And now we can solve for the charge. Okay, you don't want to look at that. Okay, so that's what I'm getting for the Coulomb. Let's see if I can make it look better. Yeah, okay, I got it. 4 times 10 to minus 8 coulombs. Let's see if that matches what we have here. We're talking about 40 nanocoulombs. Yeah, that's 40 nanocoulombs. That's right. 40 nanocoulombs is 40 times 10 to the minus 9. Right? And I got 4 times 10 to minus 8. Is the same thing. So that's... You can repeat the problem for the double of the charge. Electric field due to a point charge, you already know that, right? That's the equation for the electric field of a point charge. And that's how it looks like in vector format. The points that are closer to the charge has a more intense electric field. That's why the arrow is longer. As you move further and further away, the intensity of the electric field, the length of the electric field vector, decreases. Principle of the superposition, we already did that. You know, any vector obeys the principle of superposition, right? Why did the principle of superposition? Right in here. Okay, I use the principle of superposition. Electric field due to one charge, electric field due to the other charge, they sum vectorially. Okay, electric field due to 2-point charges. Okay, let's do this one too. It's a good one. I already did it in a qualitative fashion, right? Positive and negative charge along the y-axis. But now we are going to do it in a quantitative fashion. Let's do that. I'm going to use the same drawings that I was using here. One charge is positive, the other charge is negative. Let's go back here. Let's see, I can take advantage of any of those. Yeah, let's take advantage of this one right here. Well, this one doesn't require a y-axis because the charges are lined up along the x-axis, and not only are lined up along the x-axis, but also I want to know the electric field along the x-axis as well. Okay, this charge is going to be positive Q1. I'm going to put, lower Q greater than 0. Uh-oh. You have to do all of that, okay? When you're solving a physics problem, you have to do all this trouble. Doing that by hand is much quicker than doing that by computer. The advantage of doing that with a computer is that I can save it for later on. And it looks nice as well. And the other charge is what? The other charge is a negative charge, Q2. I'm going to put that here. Q2 less than 0. Like that. Oh, don't do that. The software always think it at the beginning of the line is capitalized. We know the distance between those two charges, right? Let's set this one as being my origin, and I'm going to call the distance between those two charges A. And here I'm going to put as being the origin 0, the origin of my x-axis. We know what the value of the charge, we know the separation of the charges, and you know the distance of point P, 0.8 meters from the charge 2. What are the magnitude and direction of the electric field at point P? Is it to the right? Is it to the left? Or any other direction? Okay? So I'm going to put here a point B somewhere down the stream here. And I'm going to mark. I'm going to take advantage of this one here. Here you go. Here you go. Black. Here you go. Find the electric field at this point. What else is asking? Here you go. What are the magnitude direction? Okay. So we're going to do now the superposition principle. First, we are going to find out the electric field of the negative charge, right? So let's use this arrow here to illustrate the electric field of the negative charge. I'm going to put in a different color. So that's the electric field of the negative charge. I even going to put E2. I'm going to illustrate that with the purple color as well. And then there is the contribution of the charge number 2. I'm going to put that a red color. I'm going to assume, because this charge 2 is further away from charge 1, so I'm going to assume that the electric field of charge 1 is going to be shorter, less intense. But I cannot tell you that for sure until I do the math. Put that in red color as well. Here you go. That's the x-axis. Here you go. That's the drawing. Okay? That's the drawing. I'm going to put that B as my X. I think my X is too small. Here you go. Doing those things in real time for you. And then we can start playing the movie too, right? Now let's go ahead and get the electric field. Okay? So go to my favorite program, go example electric field, here go this one, I forgot what's the example, here go example electric field, example 16.6. So we have electric field of 1, we have electric field of 2. Electric field of 1 is positive in the positive x direction, right? Q1, KQ1 divided by R1 square, okay? It's in the positive direction, so I'm gonna keep a positive value here. Oh, by the way, electric field 2. I'm just gonna copy and paste it here. Okay. I don't need to worry about the sign of this electric field because my Q2 is already negative. Remember that? So I don't have to worry about putting the sign in there. I'm gonna write down Q1. What's Q1 value? 0.6 microcoulombs. 0.6 times 10 to minus 6 coulombs. What about Q2? Q2 is a negative value. Q2 is minus half. 10 to minus 6. Let's see if it's 10 to minus 6. Yep, 10 to minus 6 minus half times 10 to minus 6. So I'm going to put those two here at the top. Right here. My K, you should have memorized that because that's easy to remember, right? 9 times 10 to the 9. Now we need to know what's the unit. Is Newton what? Newton per Newton per coulomb times meter square. Right? That's what K is. Did I get it right? No, I don't think I got it right. Okay, it's just Newton meter square. Right. Gotta be only, let's see here, let's see. Should be Coulomb square. But I believe it's Coulomb square. Yeah. That's right. You gotta be Newton meter square per Coulomb square. Take a look at your book. This is Coulomb per meter square. Electric field is Newton per Coulomb, right? So you must have a Coulomb square right in here to cancel out the Coulomb from this charge. So let's place it right in here. What about R1? R1 should be equal to A plus B, right? Remember that from the drawing? A plus B. R2, what's R2? R2 is equal to B. But then we also have to put the values of A and B. I didn't put the values of A and B yet. So let's put the values of A and B now. A is equal to, go back to the book, 0.4 meters, and the other one is 0.8. 0.4 meters, B is 0.8 meters. Right in here. I'm going to put that electricity. So it looks like we have everything. The net field is going to be E1 plus E2. That's what we want. So let's start replacing it. Here go E1 and E2, right? Here go. That's the equation that we got. E1 and E2. K. I'm going to substitute for K. That's what we get. Hopefully there is no mistake here. If there's a mistake, let me know. Then we're going to substitute for Q1. Okay, substitute for Q1 right in here. We're going to substitute for Q2. If you want to do, oh, I didn't do the math yet. See the negative sign here? Yeah, I didn't do the math because I didn't substitute for R2 square, right? And R1 square. Let's substitute for R1 and R2. Here you go. And then substitute the numerical values of A and B. A and B. Should do all the math. Oh, didn't do the math automatically yet, which is okay. So obviously, let's see what's going on. Yeah, obviously it's going to be a positive, right? Q1 is a larger charge than Q2. Let's see. Oh no, wait a minute. It's not obvious yet. It's not obvious yet because this number here may end up being smaller than this other number, right? Let's see what happens. I'm going to solve them separately first, and then we worry about the overall result. So yeah, it's going to be a negative charge, a negative direction. Even though the electric charge here has a magnitude that is smaller than this one, the distance makes up for this difference, right? The fact that the first charge is 1 meter, 0.2 away from the point makes up, this distance here makes up for that. And then we finally get, calculate, here you go. Hey, wait a minute, there's something wrong here. Why my n canceled out? Doesn't make any sense. Let's try it again. Let's try expand. Okay, now the end is in there. Something happened to the end before. I don't know what happened. So I'm getting 3,281 newtons per coulomb. Okay, let's take a look at the final 3,100. He's getting 33,000. Yeah, 3,300. Let's see if I made a mistake here. Oh no, 3,200. Okay, 3,300. That's what he's getting. Well, yeah, magnitude is the same. I'm getting a negative sign, right? Negative sign, the arrow points to the left. That's so I got the right result. So we can do that for 3-point charges too. It's just a matter of getting everything right. Okay, you can practice that at home, find the angle. Electric field lines already showed that to you. Oh yeah, here you go. Electric field lines. What you have to know about the electric field lines? You know, electric field line is much convenient to draw than a vector line, okay? Than a vector field. I showed you a representation of the electric field lines right in here, or right in here for a positive charge. It's a very convenient representation. Let me shorten this one up a little bit. This one is going to be shortened up. There we go. So what does this representation mean? It means that the closer the lines are spaced, the stronger the electric field is. Okay? The electric field here is stronger than the electric field here because the lines are separated, the distance of the lines are further away. And you can have all sorts of electric field line representation. For instance, depending on your charge distribution, you can have things more complicated like this one. This one that you see here is the electric dipole. Okay? Nearby the positive charge and the negative charge, the electric field is weaker, is stronger, because those lines are close together. It's not exactly an electric dipole because this one is +3 and this one is -2. An electric dipole is the one that the electric charge has the same magnitude. Okay? Here, an arbitrary distribution of charge, let's say, generates a field like that. So we can tell you from this electric field line that the magnitude of the electric field here is stronger than the magnitude of the electric field here. The separation, because the separation of the lines is greater. That's the interpretation that you have. But it's impossible to have electric field lines crossing one another. Okay, that's not possible. They don't cross each other. Field lines, rules illustrated, the electric field direction at points P and R, yeah, is tangent to the line. The electric field is tangent to the line. That's what he's mentioning. The magnitude of the electric field point P is larger than the magnitude at R. Okay, why that again? P, okay, here is, oh, right in here. Magnitude here is more than that because the lines are closer together here at P. Okay, if 12 lines are drawn starting point charge, then 8 lines must be drawn. Okay, that's C. 12 and 8 because this charge has less, is smaller than this other charge. That's why he's drawing 1, 2, 3, 4, 5, 6, 7. Oh, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Whereas here we have 12, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because here the charge is greater than this one, we have to draw more lines by 1.5 factor. Because 3 divided by 2 is 1.5. But you cannot have electric field lines drawn like that. Something like that doesn't exist. Okay. Field line for a point charge, I did that for you. The field lines in reality is a three-dimensional type of electric field lines. Electric field due to the dipole. Here's just a representation in the two-dimensional space, okay? But in reality, those electric fields are extending into the three-dimensional space. Okay, here we go. If you have a shell like this one, a charged shell, you're going to learn soon that you must not have an electric field here inside. That's because this field moving from the right to the left is going to cancel this field that's pointing from the left to the right. Okay? So the electric field of a positively charged shell is going to be 0. inside, on the inside, but not on the outside. That's what we have for this section. And I want to fill you in what you have to worry about this section. Here you go. Capacitors, electric potential. This is charge. This is, yeah, going to for chapter 16. For chapter 16, you must worry about the following sections. Section 16.1, (16.2), 16.3, 16.4. We're going to do 16.5. We didn't do that yet, but we're going to do conductors in electrostatic equilibrium. We can, yeah, we're going to do that, qualitatively. And we're going to look at that also at Gauss' law for electric fields. Okay, the last section is a very nice way, very simple way to determine the field of different charge distributions. So think about that, and I'm going to terminate this section right now. You can look at this video later on, and I will create another video for the other sections that I didn't cover. Okay, so see you soon, and let me know if you have any questions. Bye bye.